morning, everyone. Welcome back to class. So we're in the end of chapter 3. We're going to be wrapping chapter 3 up today. We'll be starting chapter 4 on Wednesday's lecture. Just a timeline of our events leading up to midterm 2. We have all of this week and all of next week for lecture, and then we take midterm 2 the week after that. So we have an activity this week in recitation over chapter 3. You'll get an activity next week over chapter 4. We'll be, I think, have plenty of time to cover through chapter 4 into next week, and then into the Monday before midterm 2. A couple weeks from now, we'll do that 7:15 review again, so I'll remind you guys and send an email and all that about that soon. There'll also be a Thursday night review similar to the midterm 2 review by another instructor, Dr. Wynn, Dr. N. If you're interested in that, I'll send information about that too. So just kind of thinking ahead towards midterm 2, but we got a little bit of time before we get to there. Let's get back into chapter 3. So we're in the last section of chapter 3 on limiting versus excess reactants. And so whenever we're picturing a reaction, let's just have a really generic reaction. Say A plus 2B goes to C, just to have kind of a generic reaction. We could have an actual reaction here too, but just thinking really simple, just in terms of, a reactant A versus needing two B's to be present to react to form a common product. This would happen to be a combination reaction if you're thinking of the terminology from the first part of chapter 1. But the idea of limiting versus excess reactants is I can mix together whatever proportion of A and B I want to mix together. I could take 100 parts of A and like 2 parts of B. And I'm just only going to have one of the parts of A react and have the rest of A remain. And so when I think of taking, the ratio of 1 mole of A reacts with every 2 moles of B that are present to then form 1 mole of C, means that if I mix together some different ratios of A and B, one of them could just be simply left over as the excess reactant. And so the excess reactant, of course, is the one that remains after the reaction completes. And the limiting reactant is the one that is consumed during the course of the reaction. So completely consumed during the course of the reaction, goes to 0 moles. And so that's the one that limits how much product can be formed. So that's what the word limiting comes from, is the reactant that's completely consumed during the reaction is the one that determines how much product should be made during the course of the reaction. So for example, you take, 10 moles of A and 30 moles of B. For every 10 moles of A, we only need 20 moles of B to be present. So in this case here, B's are excess reactant because we have 10 moles too many. So 10 moles remain after A completely reacts. So for 10 moles of A, we need 20 moles of B. They react together, they go down to 0, and then we end up forming 10 moles of C. Okay, so we'll do a bunch of examples of actually putting numbers to this here in a minute and looking at different ways of thinking through the math of solving this. We can think those BCA charts, we can think about just setting up dimensional analysis steps, but we'll see that in the context of a few examples that come in the next few slides. But before we get there, let's talk about the theoretical yield. That's the one that we'd be calculating from our stoichiometry. That's the yield we expect. That would be, for example, here 10 moles of C. We'd expect to form during the course of the reaction of 10 moles of A and 30 moles of B. So that's our expected yield. Let's say we only get 9 moles. Let's say we run this reaction. We're supposed to get 10, we only get 9. A lot of times our actual yield is lower due to errors or side reactions. So maybe there's some other reaction that takes, A and B and makes them form some other compound D or something, and that happens some small percent of the time. So our yield technically should never go above 100%, but of course there's sometimes experimental error. Maybe we're doing these reactions in water and we're supposed to dry C, so it's perfectly dry, but we have a little bit of water left over. But the yield of the actual compound C should never exceed 100%. And then the reason why we might not get 100% are side reactions or just maybe some experimental errors. Maybe we just lost some in transferring between flasks or whatever in the laboratory. Then we express our percent yield as our actual yield. Divided by the theoretical yield times 100%. So for example, we're supposed to get 10 moles of C, we only get 9. So that would be a 90% yield. And so our yield calculation is just what did we actually get, what did we expect to get following our stoichiometry. And the key here is that our theoretical yield is the one that's linking up to that limiting reactance, the one that's linking up to our stoichiometry. So the theoretical yield's the one that if you follow through the stoichiometric steps in the reaction, it's the yield you're supposed to have gotten in the reaction. Like I said, we'll do a bunch of examples that show and highlight these ideas. So let's get into some of those examples so we can see some numbers here throwing together these ideas. So let's say we take 15 grams, 15.0 grams of N2, 2.50 grams of H2. They react together according to this reaction here that says for every N2, it reacts with 3 H2 to form 2 NH3. And so just remember, our reacting units are one of two things. It's either molecules or moles. So we can either think of this as a distinct molecule of N2, so 2 nitrogen atoms with 3 molecules of H2. So maybe we're literally picturing an N2 molecule. Maybe we're picturing 3 H2s as distinct molecules, and then they're forming, NH3s, 2 of them. So we can picture that in our mind, I think, pretty easily, that on the molecular level, you can think of the coefficients as molecules, or you can think on the large side, you can think the coefficients are for every 1 mole of N2, we react with 3 moles of H2 to form 2 moles of NH3. So we can think the mole ratio as well. Now, we can't really think the mass ratio, right? Hopefully it's pretty obvious that the ratio of the grams of nitrogen to hydrogen don't work out according to the coefficients. We have to convert those to their mole quantities. So the masses, the ratios don't work with the masses because each compound has a different molar mass. So when we're asked the question, which reactant is the limiting reactant, and then how much product forms, we can think of a way or a couple of ways we might solve this problem. Now I'm going to do the way, and sometimes students get annoyed with BCA charts, not entirely sure why, because sometimes they're harder to set up, but the thought is there of what goes on in the problem that we can then think about and hopefully better understand when we're doing a dimensional analysis step. So we'll do this problem 2 different ways with 2 different approaches. Let's start with the BCA chart. Now the only thing with a BCA chart, when I go to plug in, I want to put moles into it, not mass. So I don't want to necessarily write 15 grams for N2. I want to write the number of moles of N2 and work that out. Pretty simple, right? It's just 15 grams, and then I have to use the molar mass of N2. So the number of grams of N2 per mole of N2 would be 28.02 grams per mole of N2. And so sometimes we get caught up on when do I use the mass of N versus N2? Well, it's moles of N2, so that's why we're using the molar mass of 2 nitrogens. So 2 nitrogens mass in the periodic table is 28.02. So 15.0 divided by 28.02, I get 0.535 moles. So I can write that over here for my N2. Now, the reason that I have to write these out and do this math is probably why fundamentally we wouldn't do this on an exam, or once we get exam savvy, we're gonna have a faster way to solve the problem. But the BCA chart, I think, really helps us see the math behind the problem and just how we're setting it up, why we're setting it up, and how the math works. But I'm just doing the same step for H2. It's 2.50 grams of H2, and then it's 2.016 grams per mole of H2. So that's the steps to find the number of moles of H2. So I get 1.24 moles. And then, when we do most reactions, we're starting with the reactants, not the product, and we're going to let the reactants react until we make as much product as possible. So whenever we then say, you mix together this reaction and they fully react together, means that they form as much product as possible. Now our change goes minus x, minus 2x, and then minus 3x. I'm looking at my coefficients in the reaction to determine what I write here. So minus 1x because there's 1 N2, minus 3x because there's 3 H2, and then plus 2x because there's a 2 in front of ammonia. Now the thought here is this, is for every mole, for every 1x of moles that I lose of N2, I have to lose twice as much of that quantity, or 3 times as much quantity of H2 because of the 3 in front of the H2. So if I lose 1 mole of N2, I have to lose 3 moles of H2 and then in their place I form 2 moles of NH3. And so these coefficients here are just coming from the numbers in front of the reactants in the balanced chemical reaction. And so also, if you just look at the moles, I think you can see the answer. Like if you think of the ratio of 0.535, I need twice as much N2 to react with all of that, and I have that much. So for 0.535 moles of N2 to react, I need, 3 times, I keep saying 2 times as much H2. It's 3 times as much. I actually don't have 3 times as much H2. 3 times 0.535 is 1.5 moles. I only have 1.24 moles of H2. So it seems like H2 is the one that has to go to 0. So in our BCA chart, it's kind of like which one of these two goes to 0 is our question. So one of them has to go to 0 or both. If we have the perfect stoichiometric ratio, if we have the right 1-to-3 ratio, they both will go to 0. But for the reaction to finish, one of them hits 0. And if there's some left of the other one, then there's going to be something left here after the reaction completes. And so I think we have a pretty good prediction that H2 is going to be the one that's 0. And so to then say if that is 0, then I can solve for X. So if H2 really goes to 0, and I know it was 1.24 moles originally, and it minus 3X equals 0, can I solve for X? I'm pretty sure I can. So X is just going to be equal to 1.24 divided by 3, which is 0.413 moles. And then when I take X over to my N2, and say if I want to calculate my N2 that remains, it's the 0.535 minus X. So the N2 that remains after the reaction is equal to 0.535 moles minus 0.413 moles, and that's 0.122. And for some reason, I always screw up math that's simple right in front of me. I'm going to double check that. Yep, 0.122 moles. And so that's the amount of N2 that remains after the reaction completes. So we've consumed 0.4134 moles of the N2 that's left, gone into forming the NH3, and then we're left behind with 0.122 moles of N2. And so this reaction takes place, goes to completion. We've taken all of the H2 that was present and have lost it all into the form of NH3. We've formed now 3X, 2X. I keep interchanging my 2's and 3's here. So 2X is the amount of NH3 that forms. And so 2 times X, 2 times 0.413, is equal to 8.26. So that's the quantity of product that forms during the course of this reaction. So I can calculate and see H2 is completely consumed. I have some N2 remaining, and then I form 0.826 moles of my product NH3. Now, the question here is asking how many grams of the product forms. Well, let's just do a gram to mole conversion. Let's just say, let's convert this number of moles of NH3 using the molar mass, number of grams per mole for NH3. So it's just 14.01 for nitrogen plus 1.008 for the hydrogens times 3 of them. So that's 17.03 grams. So 0.826 times 17.03 is 14.1 grams. So let's think about this from the start. We took 15 grams of N2. We took 2.5 grams of hydrogen. That's 17.5 grams of total reactants present. After the reaction completes, we took that 17.5 grams and turned it into 14.1 grams of NH3. And then we're left behind this many moles of N2, 0.122 moles of N2, times, so if I take this molar mass here, times 28.02, gives me 3.42 grams. And if I add that to the 14.1 grams, I get my 17.5 grams that I started with. So we've started with 17.5 grams of reactants. We've just now turned them into 14.1 grams of products, and then still 3.4 grams of the remaining reactant that's still present after the reaction completes in the form of N2. So one last thought, other than thinking about this problem in a whole different way, with a whole different math step. So we're going to solve this problem a second time, but maybe through a set of steps that you'll see are a little bit easier, and maybe the way you were thinking of solving it. But this is a way of just trying to think about, there's reactants, we lose them, one of them goes to 0, we can try to think about which one it is, we can make a good prediction. We found out that our prediction was right. If we were wrong here, if we were mistaken in identifying the limiting reactant, if I set this to 0, and if my X turns out that it makes the other reactant go negative, that's what would happen if we chose the wrong reactant. If I had gone through the tasks of setting X equal to 0.535 minus X, if I set the N2 to 0, notice that my X would have been 0.535. Notice that 1.24 minus 3X would have been negative. If you get a negative amount remaining, we've misidentified the limiting reactant. We just need to go switch to the other reactant being 0, and we should be able to get the right answer from there. So hopefully this chart helps you understand the behind-the-scenes math behind what could be a second attempt to solve the problem using dimensional analysis. And so the dimensional analysis approach to me is easier than probably all this work here that we just went over, but without understanding what we just went over, sometimes the math in this dimensional analysis step may not be understood or may not make sense to you why we're doing these steps. So in our dimensional analysis, what I can do is I can set up problems. I can set up the mass of NH3 that I could make if I consume all of the nitrogen. So let's assume from nitrogen that we make as much product as you can possibly make with that N2, assuming you have an excess of the other reactant. And then let's go through the problem a second time where you make as much product but consuming all of the other reactant. And again, assuming you have enough of the other reactant to react with it. Okay? And so this is probably the way you might remember solving this type of stoichiometry problem from high school, where you might say, grams to moles for N2, so our gram to moles, 28.02 grams per mole. For every 1 mole of N2 that reacts, we form 2 moles of NH3 according to our balanced reaction. So again, I'm just looking at my reaction, looking at the coefficients. For every 1 mole of N2, we get 2 moles of NH3. Now this step here assumes that you have enough H2. This assumes that you have enough hydrogen to form this much product available. So this step here is assuming we have enough hydrogen for the hydrogens to be formed onto the NH3. And then our 1 mole of NH3 has that molar mass of 17.03 grams. And so if we calculate this quantity, let's actually calculate that in a second, but let's write out the steps for H2. For H2, it's just 2.016 grams per mole of H2. So just using the molar mass of H2. And then for every 3 moles of H2, we form 2 moles of NH3. I've gotten them right this time. So that's just the 3 in front of the H2, the 2 in the front of the NH3 from our reaction. And then for every 1 mole of NH3, the molar mass there is 17.03 grams. Think back to that one slide we had where molar masses go grams to moles. So the mass of a substance to its molar mass uses its molar mass. The conversion from moles of one thing to another uses the coefficients in the reaction. And then to the mass of the other thing is using its molar mass. So we're just using molar masses and our coefficients in the reaction. So let's run through the math. So 15.0 divided by 28.02 times 2 times 17.03 says if we have all of the nitrogen react and we have enough hydrogen to form our product, we would get 18.2 grams of product. Now, right off the bat, you should say this might be a problem because I only had 17.5 grams of reactant here. So we don't have 18.2 grams of reactant. I only have 17.2 or 17.5 grams. We just created mass if we actually think this would be the right answer. So this is probably something we're thinking is not going to be the right answer. So we went through it a second time with the other reactant, so 2.5, divide by 2.016, times 2, divide by 3, and then times 17.03 gives me 14.1. And so when I get these two answers here, I have to choose the one that's lesser because when I hit 14.1 grams, I run out of hydrogen. So at the 14.1 gram point, our H2 has been completely consumed, it's gone to 0. So one of the thoughts here is when this step here, when we're using this math step, sometimes we miss that we're saying when 3 moles of H2 are consumed and replaced in the reaction, we get in their place the 2 moles of NH3. So we're losing the H2, we're forming the NH3, so the H2 is gone when we get to this quantity of NH3. It's been consumed. So the thought is really this step here, in that VCA chart's kind of hopefully in our mind of we're losing the H2, gaining in its place the NH3. So at 14.1 grams, we've completely consumed the hydrogen, and then we're going to not be able to make any more product from that point just because we've run out of the H2. So we can't get to 18.2, we're gonna stop at 14.1 grams of our product and then have the other reactant, the nitrogen, left over as the excess reactant. So this step here is another way. So the ways to identify a limiting reactant are, 1, look at the moles, 0.535 versus 1.24. What's the ratio? You can think about mole ratios. 1 to 3, it's less than 1 to 3. So you can think about calculating moles, comparing the quantities, eyeballing it that way. You could also set up a BCA chart, solve for which one's 0. You could also calculate how much product you need to react, or how much product can form off of each reactant. The lesser amount of product comes from the limiting reactant. So we have a lot of choices for determining limiting reactant that hopefully all make sense. If we get really good at stoichiometry problems on a test, in our mind really quick, we come up with the way that's fastest. Now, if you come up with the fastest way to solve the problem, you don't get any bonus for that on the test other than having more time for other problems. So if you can be efficient on an exam, that's great. But if you have 3 or 4 ways you can solve a problem, then at least you have one way you can hopefully find to do the problem on the test that makes sense, that gets you to the right answer, even if it takes you a minute or 2 longer. Okay, so we do this reaction here like we did before. So we're supposed to get 14.1 grams as our theoretical yield because that's what we found previously. So this is our theoretical yield. So coming back to the concept of theoretical yield, we would say theoretically this is how much product should be yielded in this reaction. So if the reaction only yields 12.2 grams of ammonia, what's the percent yield of the reaction? So the percent yield, it's the same ratio. It's the same 15 grams and 2.5 grams in the previous page. So my percent yield is my actual yield, 12.2 grams, divided by what I should have gotten here, 14.1 grams, times 100%. So percent yield, pretty straightforward. It's just saying we're supposed to get 14.1 grams. That's according to the stoichiometry of the reaction. If we run this reaction in the laboratory, we find we only get 12.2 grams. Then our percent yield is just not quite 100%. And it would be, in this case, 86.5%. So the yield of the NH3 shouldn't go above 100% because we're creating matter at that point. But of course, there could be experimental errors. So experimental errors all kinds of things can happen if you just have an error in the laboratory. Okay, so now, same reaction, but slightly different question here. And what I want to think about is with this question here, is almost introducing another way to solve the math in this problem using dimensional analysis that also identifies the limiting reactant. So we answered this question with our BCA chart previously. So you might remember in the BCA chart, we determined that H2 was limiting, N2 was excess, 0.122 moles of N2 remained. Let's try to forget about that. Let's try to say, we see this on a test. If I see this as a test question, can I use dimensional analysis? And if so, can I find the fastest dimensional analysis way to try to solve this problem? And so let's assume we didn't run through the math already. So maybe we don't know what the answer is. Which reactant is limiting versus excess? using a dimensional analysis approach, I would say just take one of the reactants, just pick one of them. I'm going to pick the wrong one. But I'm going to say how much hydrogen do I need to react with all of the other reactant, the N2. So the way we could solve this problem using dimensional analysis, we could do the same approach. If we see this on a test question, we have to identify limiting versus excess. We could make ammonia off each, see which one's lesser, and then go figure out how much of the excess reactant remains by how much of it reacted. But if we ask the question, or just by dimensional analysis try to say how many grams of hydrogen fully react with the N2, then we're just like off using dimensional analysis here, where 28.02 grams of nitrogen present in 1 mole of N2. For every 1 mole of N2 that reacts, we need to react with it 3 moles of H2. And then for every 1 mole of H2, that's 2.016 grams. And so let's calculate this here. If we're lucky, which we're not lucky, but I'm intentionally choosing the one that I know is wrong just to show you what this will look like. If we're lucky, we get an answer that's right. We don't even have to run through it a second time. This is an example. You don't necessarily need to do it both ways like we did for making NH3. We had to run that. If we're doing dimensional analysis for product formation, we have to make product from both reactants to see which one's lower, to identify the limiting reactant. Here I'm just saying how much reactant do I need to react fully with the other reactant present. I get 3.24 grams of H2 would be required to react with all of that N2. So what this dimensional analysis set of steps here is trying to work out is how many grams of hydrogen do I need to be present to fully react with the present quantity of N2? It's more than the H2 we have available. So we only have 2.5 grams of H2. And so we can't get here. Now, when you do dimensional analysis, this is where I say you have to have like a thought of what's going on, because you could take 3.24 minus 2.50 and get a number that's positive, but that math doesn't make sense, right? Because you're taking the amount that you needed to react versus what was available. What you'd be calculating there is the mass of hydrogen you're missing. The mass of hydrogen that we need to think about here is the initial quantity, 2.50, that's the before amount, minus the change, which this case would be 3.24 grams, and then the after would be negative. And so negative what, negative 0.74? Yep. So we'd have 0.74 grams negative after the reaction completes. That doesn't make sense. You know, we can't go negative in quantities. And so we need to think here, if we're thinking BCA chart, even along with our dimensional analysis steps, at least in our mind, we can see that this amount of H2 is clearly impossible. And so we just run through it a second time, see how much N2 we need to react with the available H2. So grams to moles for hydrogen. For every 3 moles of H2 that react, we need 1 mole of N2 to be present to react with it. And molar mass of N2 is 28.02 grams. So we go 2.5. Divide by 2.016, divide by 3. Times 28.02 is 11.58, 11.6 grams. And so that's how much N2 that I need to react with the N2. Now on a test question, if this is a test question with multiple choice answers, then one of the choices is probably how much N2 remains after this reaction. Almost always the choice will be 11.6 grams will be there to choose from. That's not the remaining N2. That's the amount of N2 that reacts with the H2 when the reaction goes to completion. So if we're thinking, the N2 that's initially present before the reaction takes place, 15.0 grams. My change is 11.6 grams. That's the amount that reacts. And then the after quantity that's present, 15 minus 11.6 is 3.4 grams. So I have 3.4 grams of that 15 grams of N2 remaining after. So the amount of N2 that remains is 3.4 grams. And so this thought here, we can be doing this math or this thought in our head too. You know, like this is something that when you get to a point in a dimensional analysis step where you don't understand why we're subtracting something from something, it's like go back to the BCA chart for a minute, just rewrite the BCA chart, think about that, and if you're good with it, then that's just what we're using right here. So before change after charts, helpful, I think, to understand their setup, not necessarily required in most problems that we even write out or necessarily go through the steps of considering each one of those steps, but if we can, it'll help us understand if we understand that process, we can understand the math better behind the dimensional analysis approaches. So once we get through an example or two, we're going to get to a point where we almost need to like leave this topic and let it like kind of settle and then practice it again. This is definitely a topic where if we just go through like 10 examples right now and just like hammer this into the ground, we're going to like forget it still. You know, this is a topic that's pretty straightforward, but it's one that you almost need to make sure that you revisit it a couple times to make sure it sets in. So, and it's also a topic we're going to keep coming back to. There's so many topics of chemistry that have some underlying aspect of stoichiometry. So good news is we're going to keep reinforcing it in a bunch of other chapters as we go along, but of course it's really important. You need it. So just know it's going to take just probably some practice to make sure you're good at running through these problems and hopefully don't run into any obstacles. And there's so many different variations too in questions. You'll see there's tiny different ways we can vary an example, but if you think about the different approaches we have available, we ought to be able to come up with a way to solve the problem. So let's say we have H2 reacting with an unknown amount of O2. 76 grams of H2 forms by the reaction. How much H2 remains and how much O2 reacted? Well, let's think about this for a minute. So let's make sure we write out the reaction. We have H2 and O2. They're forming water. We know to balance here, we're going to go 2 in front of water and then 2 to balance the hydrogens. If I go the BCA chart, let's think about this for a minute, because this is actually kind of an interesting BCA chart because we're told we have 12 grams of hydrogen. I'm going to write that up here just to know that I should convert that to moles into my BCA chart. So if I take 12 grams of H2, divide by 2.016. I don't know if I need to write that out. Does anybody want me to write out the steps for the moles of H2? Because we're just using the molar mass. So when I come up with 5.95 moles, that's just taking the grams and then the grams per mole for H2. But now, I don't know how much O2 I have. I have some clearly because I'm going to form water, but I don't know how much O2 I have initially. And then before the reaction, we have 12 grams of H2, an unknown amount of O2, and then 76 grams of water forms by that reaction. So initially no water, and then my reacting coefficients here, for every 2x of hydrogen I lose an x of O2, and I gain 2x of water. And again, just coming from the coefficients in the reaction. And then after the reaction, I get 76 grams of water. 76 grams of water. Water is 18.02 grams. So just converting that to moles, that's 4.22 moles. I have to put moles or molecules into the chart. And maybe that's confusing, but just remember the gram isn't the reacting unit, the mole or the molecule is. So that's why I don't want to put 76 grams into my chart because it might confuse me. X doesn't really relate to the 76 grams, it relates to the 4.22 moles. Okay? And so once I write this step out, do you see how the answer is almost right in front of us? That 0 plus 2x is equal to 4.22, I can solve for x. You know, I know x is 2.11 just from that step there. 2x must be equal, so 0 plus 2x is equal to 4.22 moles, so x is equal to 2.11 moles. It's like right in front of our face, you know? So like if we set up a BCA chart, now this is a weird one. This is one where we didn't know one of the reactants masses. We just know that hydrogen is how much hydrogen was present, that we had some oxygen that's unknown to us how much there was, and then we know how much water is being formed. How much water is being formed allows us to calculate the moles of water that had formed. From that, we can determine what x is equal to in our chart. And then when we go over to here, minus 2x, the amount of hydrogen that remains after the reaction, can we calculate that? I think we can. So 5.95 minus 2x, or x is 2.11. So if x is 2.11, sorry, I'm going to rewrite that just so that this is really clear here. That 5.95 moles minus 4.22 moles is 1.73 moles. That's the amount of moles of H2 that remains in terms of a mass times 2.016 grams. It's 3.49 grams of H2. Now, interestingly, that lets us choose the answer because that's the only answer that had that as the mass of hydrogen that remains. But we can also calculate the amount of oxygen that had reacted, because the oxygen mass that reacted is just X. So 2.11 moles. So the amount that had to have reacted here, we had to at least have 2.11 moles, so I could lose that quantity and go to at least 0. There could be oxygen. Maybe we stop this reaction halfway. But in terms of oxygen, there probably should have been 2.11 moles present to react and form this amount of water. And so if this is going to 0, then this would mean we had 2.11, so we go minus 2.11 down to 0 to stop that reaction, presumably. And so the amount of oxygen that reacted here is 2.11 moles of O2. That's 32 grams per mole. So 2.11 times 32.00, 67.5 grams. So occasionally there's a question where they, whenever this question was authored for a test, this is an old test question, the thought was really constructing a BCA chart for this test question. Now, at the same time, I don't want to keep beating this into the ground, but there is a dimensional analysis way to solve this problem. But it just requires us to ask a question that we can answer with the information available. That's the tricky part of dimensional analysis is there's so many different questions you can ask and answer, and finding the right one or the best one that gets you towards the answer is sometimes not always easy to find, especially if you have no concept and conceptual understanding of the BCA chart. Once you understand the BCA chart, I think you could look back at this chart, having not even done the chart example, and say, well, from how much water is formed, I should be able to figure out how much H2 had reacted with it. So again, not to necessarily keep solving every problem two different ways, but our approach to here might be to have said, well, how many are required to react with enough oxygen to produce that 76 grams of water? So I think we could be off and running. It's just we have to find kind of a question like this to answer, and we have to then think this is the amount of hydrogen that reacts. This is our change quantity. This is the amount that reacts with O2 to produce the quantity of water. So the question, when we work this out, it's like saying how many grams of hydrogen are required to be present and react fully with oxygen to yield 76 grams of water. 18.02 grams per mole of water. For every 2 moles of water that form, we need 2 moles of H2 to be present, just the 2 in front of each of the reactants. And then for every 1 mole of H2, that's 2.016 grams. So even though I like the chart here, it was pretty straight. Once we put the numbers in the chart, the answer was really right in front of our face as long as we understand it. It's really pretty easy this way too with the dimensional analysis. So I just go 76 divided by 18.02 times 2 divided by 2 times 2.016 is 8.50 grams. And the amount that remains is the amount that was initially available, 12 grams. So 12 minus 8.5 is 3.50. So 3.5, 3.49, depending on which way you go through the math. So 3.5 grams of hydrogen remains after this reaction completes. And so we're getting back to the same answer here. And then you can even say, well, how many grams of oxygen are needed to fully react with this quantity? If you just go through the problem of saying, well, the number of grams of O2 from the same approach, (18 grams per mole of water. And then for every 2 moles of water that are produced, we need there to be present 1 mole of N2, or 1 mole of O2. Now I'm confusing N's and O's instead of 3's and 2's. So 1 mole of O2 from our balanced reaction. So that's the coefficient in front of O2 versus the coefficient in front of H2. And then 1 mole of O2, 32.00 grams. So 76 divided by 18.02 divide by 2 times 32.00, 67.5 grams. Now, the like A+ level thinking on a test is which of those ways is fastest? You know, but probably still the A+ way. I would still say A+ thinking is just a way to get the answer is still, to me, A+. You know, so like if you're thinking, well, I'm going to set a chart up even though it might take me a little bit longer, but I know I'll understand the problem if I do, that's great thinking too. That's certainly going to lead you towards the right answer. I think the way to miss this question on a test is to kind of like throw a dart and say, I'm going to calculate something with dimensional analysis and not really understand what I'm calculating and get a number that I'm not entirely sure what the meaning of the number is. With dimensional analysis, you'll get a number at the end when you put it in the calculator. The question is, what does that number mean? Is it the hydrogen initial? Is it the hydrogen that changed? Is it the hydrogen that remains after? You know, like there's a lot of different ways you can throw numbers together that lead you to a result that you may not be sure what the meaning of the number is. The meaning comes from the BCA chart. Okay, let's come back to where we kind of started. We started with a particle diagram question. Let me throw this one to you guys. This is actually an old exam question. Most of these questions are old exam questions, but this box here shows 6 fluorine molecules, 6 chlorine molecules. To be fair, it doesn't matter which color shading is which, right? Because one of them is the Cl2, the other shading is the F2. There's an equal quantity, but they're reacting to form chlorine trifluoride. And so if you have a reaction taking place, you have to balance it. I'm going to write it unbalanced. But think about how you would balance that reaction. Cl2 plus F2 goes to ClF3. And then how you can figure out which of the reactants is present in excess versus limiting quantities, so you can figure out what's present in the box after. So take a minute or two to think about this one, then we'll go over the answer. All right, so if I'm just gonna choose the Cl to be this sphere here, so my ClF3 would be this combination, so I'm gonna choose this to be my F2 color. If you did the opposite, that's fine. And so what we have take place is this collection of atoms is lost in place of two ClF3s. So we had 2 atoms of chlorine for 6 fluorine atoms. They now take the form of 2 ClF3s. And so these are gone. In their place, 2 of these molecules. And then I can do it again. And so I do it again, and I need to lasso out 3 F2s, and then just 1 of the Cl2s, and then those are gone. And so then I have 2 more ClF3s that form as distinct molecules. These are all gaseous, meaning they're just kind of independent particles floating around this box in terms of each of the ClF3s floating around the box. But now we also have the remaining Cl2s. So we have 1, 2, 3, 4 Cl2s left over. Just kind of showing somewhere random in the box they'd be located. So I have 4 Cl2s among the 4 molecules of ClF3, not asked about, but we have 4 molecules of ClF3 that formed. So our ways to solve problems, we can think particle diagrams, boxes, think of it this way. If these were moles, we can think of a box too. If I said you had 6 moles of Cl2, 6 moles of F2, and they're reacting together to form this, 2 moles of ClF3, in terms of the balanced reaction, you could take the mole quantities and represent them as molecules because they're proportional to each other. And you can think through the problem with a particle diagram as well. So you can think particle diagrams, BCA charts, dimensional analysis steps, and a variety of different ways to approach dimensional analysis steps. Okay, so from there, probably the best place now is to take a step back, look at something from early part of chapter 3, to do a quick little review on a couple topics, and then move forward into chapter 4, and every now and then we'll think back of a stoichiometry problem as we get into our next chapter, as well as you get into your studying. As we get into chapter 4, just continue doing a little bit of review out of chapter 3. Yeah.
So 6 moles are synonymous with molecules. Every time you're given one of those color charts, you should be able to do a BAC chart.
Yeah, so if we wanted to in the previous example, we could have set up a BCA chart. And if you were thinking of that, that's great too. So if you were literally thinking 6 molecules of the one, 6 of the other, you could put molecules into the BCA chart too. So if on that previous example, it kind of doesn't work if I go back in the slide in terms of the video. But so let me stay on the slide here. But if you're thinking of the Cl2 plus 3F2 goes to 2 ClF3, if you were setting this up as a BCA chart, you could have put the 6 molecules in here, and the 6 molecules in here, and then minus x, minus 3x, and then 0 plus 2x. And so then figuring out which one of these goes to 0, I think you make it the F2 because x is a number that makes chlorine not be negative. If we let this go to 0 for the chlorine, then x would be 6, and then F2s would be 6 minus 18, which doesn't make any sense. And so if you're thinking this approach, that's great. If you were also thinking dimensional analysis, you could have run through the math on that previous example through dimensional analysis too. Okay. So coming back, so one of the things from chapter 3 is just making sure we can predict products of reactions. But probably the main 2 reactions to kind of probably think that we would just expect you to have kind of memorized as a category of combustion, where you make CO2 and water. The other category is probably just the metal plus non-metal makes an ionic compound. So, like sodium plus chlorine makes NaCl. You can predict as long as we give you an alkali, alkaline, aluminum, something like that, where you can predict the charge state of the metal, the charge state that the metal goes to. It's like if you say, for example, you take sodium plus Cl2, that's the natural form of chlorine, you're going to get Na plus and then Cl minus, and you just have to balance it out from there. Or if you did this with Ca plus Cl2, then you get CaCl2 as your ionic compound, because calcium's a 2 plus. If you do this with aluminum plus Cl2, you get AlCl3, because aluminum's a 3 plus ion. So the charges of the ions, you can balance them out to make from metal plus nonmetal. So that's kind of one category of reactions I would understand from chapter 3 is metal plus nonmetals go to their ionic compounds. And depending on the element, we can predict the charges of the ion. You know, alkali we know are +1s. Alkaline group we know we're going to form +2 charged ions. Aluminum +3. Not many other transition metal group. I would really kind of consider the transition metal group we don't really know. Technically zinc's a +2. Silver's a +1. Lead's a +2. But those are kind of extraneous. I wouldn't dwell too much on those. But the other category of combustion reactions, so when we have the balanced combustion reaction of sucrose and excess oxygen, sum up all the coefficients in the reaction. So a question like number 1 would be getting at just the formula C12H22O11 plus O2 form CO2, but at least 12 CO2 to get my 12 carbons over to here. And then I'm going to need there to be water that's formed. And so for water, I need at least 11 to give me 22 hydrogens. Why does it? Well, let me rewrite it real quick. So C12H22O11 plus O2 goes to 12 CO2 plus 11 H2O. And we're just balancing the 22 hydrogens and the 12 carbons first. And then in terms of my oxygen count, I have 11 oxygens, so I'll count those as my 11 O's here. And then I have 12 O2s a part of CO2, so I have those 24 O's to go. So I need a 12 in front of my oxygen. And so in terms of oxygen, I have 11 plus 24, and here I have 24 plus 11. So my oxygen's in balance on both sides. Okay, so just to sum up the coefficients, sometimes a test question has for us to get the right balancing, just says sum up all the coefficients. So that would be a 1 for the first molecule plus 12, that's 13, and then plus 12 and 11, that's 23 over here. So that would be 26. So those coefficients sum up to 26. Oh, it says sum up the coefficients on the reactant side. So the reactant side coefficients sum up to 13. And total in the reaction. So you'll see some examples on the test will say sum up the coefficients just as a way to try to see if you balance the reaction correctly. So you'll see this type of a category of question over just the proper writing and balancing of reactions, but the key is predicting products so we can get to the right balancing. There's a question here too that gets at atoms. So the body has about 121 grams of calcium. How many atoms of calcium does this represent, or in this mass of calcium? So that's just using the molar mass of calcium. So I think I'll just allude to that example. That's just using the molar mass grams to mole from our periodic table and then thinking Avogadro's number from there. And we'll wrap up here today. So we'll get into chapter 4 next time. We'll try to sprinkle a little bit of review of chapter 3 in as we go to keep thinking about stoichiometry. All right, guys, have a great day.